Good afternoon, all. Am I audible?
Good afternoon, sir. Yes, sir, you're audible.
Okay.
Welcome back. Welcome for the FDP program, sir.
Yeah, thank you. So the participants also will come to this link or they have separate link?
Oh, no, no, sir. In the same link, they'll be joining.
Same link. So we'll wait for some time.
Yes, sir. Um, so within 2 minutes, we are going to start the session, sir.
Okay, fine.
Thank you, sir. Welcome back for the afternoon session. Respected faculty, professors, outstanding guests, and scholars, and the students from various engineering colleges. Good afternoon, one and all, and a warm welcome to the fifth day afternoon session FDP program. We aimed this FDP on recent trends in embedded systems and IoT applications. Towards this, we comprises a series of technical presentations and video demonstrations towards the platforms of VLSI embedded systems in the channels of the experiments and made the experimentation in the Z boards and Zinc boards for IoT support technologies to deploy the IoT and embedded applications. So to a way forward for this afternoon session, we have the resource person, Professor Samrat Sambat. He's a professor from Center for Advanced Studies in Electronic Science and Technology, University of Hyderabad. He has involved in several sponsored projects as investigator and co-investigator for several sponsored projects from DRDO and DST. He published over 90 reputed IEEE Springer and Wheeler journals and the conference publications too. He completed his PhD in 2004 from Electronic Science from Behempur University. Sir has joined as a lecturer in electronics in the year 2004 and continuously he made his efforts till 2010 for the School of Physics, University of Hyderabad. He is a member in professional bodies of IEEE and associate fellow in Telangana Academy of Sciences. Professor Samrat Sambat sir is a visiting professor for University of Yellowknot and Cameron for 2012 May to June 2012. His research interests are implementation of DSP algorithm in FPGA, system on chip design, signal processing for cognitive radio, spectrum sensing and channel allocation, and sensor signal processing. With this brief introduction, we take privilege, sir, to invite you for the session.
Thank you, madam. Thank you, madam, for the nice introduction. Good afternoon, all. My side is audible, right?
You are audible, sir. Yes, sir.
Yeah. So thank you, the EC department, for inviting me to give a lecture on this IoT. I could see that this is the last day or last but one day. Tomorrow also.
Tomorrow also there is a session, sir.
Correct. And so there are a lot of sessions. I'm sure that you have gone through many sessions on IoT. Intentionally, I have chosen to deliver this lecture toward the end of this TP. Reason I will discuss very clearly.
Sure,
But
sir.
at the same time, I must say that we all are now exhausted with this online FTPs. Hopefully, we'll get back to our own original way of interacting in the seminar room or classroom. I could see that the this participation numbers are also gradually decreasing. Nobody is switching video. It's become very difficult for both parties. Right? For the audience or for the participants, it is boring. And if you don't switch on your video, if you don't participate, it is equally boring for this resource person. Right? So hopefully next time when we will we'll talk in a physical seminar room. It will be more effective. But at the same time, it is not in our control. We have to be careful. We are thinking that we'll get back to our original classroom-based seminars, but one more variant is coming. We have to be a little careful, but still, let us hope that next time we'll meet in the physical seminar, right?
Definitely, sir. We
Okay.
this for the next FDP session to be offline.
Yes,
Definitely,
we
sir.
hope so. We all, the whole teaching community is now so eagerly waiting for that. In fact, in our university, we started some offline programs, but again, because of this Omicron, people say Omicron, right? We are again back to this online mode, the recent circular says. But we don't know, but still hope that we'll get back to our original mode of communication. Okay,
Sure.
so let me put my slides here. Where is that? Yes. It is visible now?
Yes, sir. Yes, sir. It's sharing
Okay,
and this.
good. Yes. So we all are talking about IoT since last couple of days. So this slide or this like talk is very basic. It goes from fundamental to little moderate research in this. But we have time till 4 o'clock. But at any point of time, if you feel bored, or if you, I will ask some questions. If you don't respond, if I feel bored, we'll stop the session there. And prior to that, also, if you think that at some time you are not understanding what I am saying, you unmute and you can speak to me. We can have a discussion there. Don't restrict that. It will be only in unidirectional mode. I will tell and you will listen. Any point of time, if you are not able to follow it, you can unmute and ask the question. I am not able to see the chat box because once I am in the PPT, I am not able to see. You can simply unmute and we can have a discussion at that point of time. Okay, so I am sure that the terminology for IoT is very clear to all of you by this time. Even if some of you have started uh, um, as fresh to hear about the IoT. But let me ask you, before I start my talk, I'll ask a question. How many of you are aware of the term compressive sensing? Can you put it at some place and somebody can tell me how many yes are there? Please put it in the chat box and I'll request the organizer to tell me how many yes are coming from there. How many of you are aware of the term compressive sensing? If anybody has knows, please put yes. We'll count yes only. Madam, any yes came from any participants? Because I am not able to see that part.
Yeah. Actually, we didn't get any question.
No, yes, sir.
No, yeah, good. So none of the participants are aware of the term compressive sensing. So this sets the scene for me from where I will start talking about. Okay, good. Um, in fact, it becomes easy for me now to explain it from the very scratch, but it is a very powerful technique, right? Okay, so there is no need to mention about me. I am Dr. Samrat Sabat, currently working as a professor in University of Hyderabad. Madam has given a very nice introduction. Thank you, madam, for giving that nice introduction about me. Okay, we have, so what are the things I will talk to you now? Most of the things are from the work of the PhD scholar K. Venkat Reddy, so I acknowledge him first. And many of the slides are, the figures are taken from different literatures to just demonstrate the concept of compressive sensing to the participants. So this is disclaimer, this is the acknowledgement at the beginning of my slides. Okay, now let us talk with, let us start little debating about what is IoT. We know that the technical definition, you are very aware that it has a processor, it is a sensor, it is a processor, it is a communication, it goes to the cloud, then does something and comes back to the customer and customer takes the action on that. But this is very technical definition. For a layman, we can see different case studies for the um, IoT. You can see there is a one cartoon which tells that we have to go, one husband tells the wife, we have to go out for dinner. The refrigerator is not speaking to the stove. You can understand how the IoT will come to our daily life in the future. Everything will talk to each other. There is no need to tell about that, how many devices are already connected, what is the prediction. I'm sure many of the speakers in this FDP have told you this thing. So, and these are all the cartoon which tells about the IoT, how it will penetrate to our daily lives. So since the refrigerator is not speaking to the stove, The stove is not switching on, so they are bound to go for dinner to the outside restaurant, right? And there is another cartoon which tells that his refrigerator is telling to the owner, I told you to pick up milk on the way. Don't you listen to anything I said? Because there is no milk in the refrigerator. It senses that and tells the owner that you get milk on the way. But again, he sees that the owner is not getting milk, so he's asking these questions. There is another cartoon which tells uh, that you can't work and chew gum at the same time, right? So somebody is observing you, monitoring you, looking at you, whatever you are doing, and he is saying that this lady is chewing gum and crossing the road, there might be an accident, so he is warning, right? There is another cartoon which tells near to that there is a shopkeeper who gives banana to the customer, and the IoT device, the weighing machine has an IoT enabled, and is asking, is that your nose or are you eating a banana? You can see that. So this person, this is IoT enabled, and he is asking this guy, this is your nose or you are eating a banana? Hmm? Another cartoon again. Your lights are on, but no one is at home. This guy, this IoT enabled device is talking to this person. He's saying that you locked your door, but there is no one, but your lights are on. Like this, there are many examples which will come into our daily life. Maybe very soon we'll all experience this. Now, what exactly is going on? What is the meaning of telling all this thing? Is that there are lots of data communication is happening. Correct? The underlying reason behind showing you these cartoons are lots of data are going from one place to other place, right? So it is all going to the cloud. From cloud, some processings are happening. Again, from the cloud, it is coming to the persons like you and me, and we have to take actions on that. So all your IoT devices are power hungry devices, I can say, because they have to transmit a lots of sensing data. Because your IoT is having nothing but a sensor processing and communication module. So whatever it senses, it has to transmit to the cloud, and there lots of processing will happen, because in IoT device itself, you will not have high-end processors, right? And the processing at many times it requires data from the different places, right? How the things are happening at different locations, geographical locations. So the best place to process that is at the cloud. Now it sets the scene that your IoT devices are power hungry devices, right? And if you want to sustain the IoT for a longer time, you have to put a bigger battery into that. Right? And the moment you put big battery, it becomes bulky. Right? So we want to have avail all these facilities, but at the less weight and less cost, affordable kinds of gadget. Right? So since we identified that it requires a lot of data to be transmitted from IoT enabled device to the cloud, now our focus is on the side how to reduce the power consumption, right? So this is the, I hope this is clear to all of you that what we are going to talk in the next 1 hour or 1.5 hours, we'll talk only about how to reduce the power consumption. Let me tell you that, right? Okay, that is one side of the story, power. The other side of the story is for the IoT security, privacy, right? One again cartoon which tells weight machine this is, and so you give me $50 or I will tweet your weight to the in the Twitter or in social media. And there is Alexa and right to that. Again, it related to privacy and security. The Alexa is telling to a young boy in the home, you lied 47 times today. I am notifying it to your mom. Right? So these are the things which is concerned to us, right? So one is power, and second is the privacy and security, right? So we are worried about these things, and let us see what technology we can use so that we will at least able to save ourselves from burning more power or um, not so much exposed to this security and privacy risks. Okay, again, before we start, last cartoon. The left hand side, it says the toaster has been hacked into thinking it is a blender. Right? So somebody has hacked the toaster and it has changed its functionality to run it fast, slow, and everything. Now it is becoming a blender. Right? So whatever you put, you imagine what will come out of that. So hacking, because all are internet enabled, all are connected, there's a good chance that the things can be hacked and the functionality will change and you will be in trouble. Similarly, let us say you have a smart toilet where this automatically it flushes, right? And somebody hacked it and continuously it is flashing automatically. By the time you go to the toilet, you will not find any water in your bathroom. So they are real life burning examples. If you don't care about privacy and security issues while building the instrument itself, we'll see all these musics later on. So to so right side, one person gets frustrated about all the things, and he is saying to his boss that boss, now all devices are 100% safe and secure, right? Then the boss asks, how did you do that? It's just impossible. Then the employer says, I turned them all off. That is the only option probably that guy found. If you turn it off, nobody can hack it. So these are the cartoons, but they're all powerful message it gives to all of us how important to talk about power. One is power consumption issue, and the second is the privacy issues when you talk about IoT. Okay, now this again, so with this fundamental thing about by knowing these fundamentals about IoT, let us talk about what are the different applications of IoT. I'm sure many of these experts might have told you this, but to make it a little bit complete, we'll say that IoT has numerous applications at different domain and different part of our life. It has a role in the consumer, home care, infrastructure, security, transportation, healthcare, retail, many, right? And these applications are exploring like anything. And we at the engineers, EC branch, or our students, they are contributing to this society by the use of IoT. And we are seeing this, how the things are changing over the period of time. And I'm sure that in next 4 or 5 years, the applications will scale up like anything. Um, Everybody will talk about IoT in that, right? Already people have started talking, but in 4 or 5 years time, everything will be based on IoT. So in one side, we are seeing that IoT has potential to penetrate into many areas and it will change the lives of ours, right? It will make us more sophisticated. The society will become more sophisticated. But at the same time, there is a threat that it takes lots of power. So the energy, if you think on that line, we have to do something on that, right? So one is the power, second is the security. They are the main two things which we need to look into at the beginning, otherwise we'll be in trouble later on. But apart from these two, there are many other issues that are also there. I'm not saying about that, but in this next half an hour, next 1 hour, 1.5 hour, our focus is on these two issues. Participants, if you are not able to understand, if I'm little speed, a little fast, you can tell me so that I will adjust my tone. Okay, so I believe I'm fine, I'm okay. Now, so this is the, now we have seen that what is IoT, in which way IoT will play a big role in our daily life, right? Starting from the very scratch level. Now let us say what is the platform architecture. We know it, but in a different context, I'm showing you this architecture. So first we'll have physical world data sensor, right? This is the sensing layer, I can say. You will have different kinds of sensor to sense different parameters, and those sensing data need to be processed, right? For example, you get noisy data, you have to denoise it. So all kind of filtering, amplification, those low-end processing, we do it in the IoT device itself. That is called as a processing layer. So first one is sensing layer, where physical sensors are available, connected to the processing layer. Next, the processed information will go to cloud, so a communication layer, right? So when it goes to the cloud, you will have again a cloud processing happens there. It extracts the meaningful information from the data, then gives the final information to the customer, right? For example, if healthcare professionals are the customer, energy management, like people like you and me who are bothered about the energy are the customer. Similarly, agriculture, farmers may be the customer. So different layers, different peoples are there who are the end product or the decision making body. So the cloud, after processing the data, will send the required information to the customer layer, and they take the final decision based on the sensing, based on the sensors, right? So it is not at the same place. If it's the same place, you don't need to send data to the cloud, but maybe they are all heterogeneous and they are scattered around all the different places spatially. So the sensors are placed at spatial location at different locations, and data comes in. You are at somewhere else, and you um, do the decision based on those data. Another thing is that there are all cross connected. One is they are spatially located, and second is they are also cross connected. For example, if you think about a smart city where an ambulance has to go in a particular road, and by the time ambulance goes, all the roads should be empty, and the hospital should be told that a patient is coming. So there are different parties to this. Everybody should be alerted before the ambulance goes, right? So there are many different verticals will be there. All verticals will be connected. Then only we say it is really IoT, or another name of that is cyber physical system, CPS. So if you expand IoT to a different layer, we say that it is cyber physical CPS systems, right? But anyway, so this kind of fundamental architecture we are clear down. We have a sensing layer, we have a processing layer, we have a communication layer, then we have a decision making layer. Right? Okay, so and remember, data goes from sensing layer till your cloud, I can say, right? So if you want to continuously monitor an event or parameter, every time you have to uh, sense it, you have to acquire it, then process it and transmit it. Keep this in mind. In EC, we know that we are acquiring, we are processing, and we are transmitting. Okay, so before I go to the technical content, there's two more simple definitions we have to be worried. One is the bandwidth, second the bandwidth, throughput, and latency. I know all of you are aware of this, but give an example. What is how you will explain bandwidth? Is the data flowing through a, this is an artery by which through which your blood flows. So how much blood can flow into the artery, that is bandwidth. But suppose somebody has a cholesterol and arteries are partially filled with cholesterol, then actually how much it is going? Really, that is the throughput. And similarly, latency, I can explain you by a pipe. If you put water in one side, how much time it takes to come out from that pipe. The delay is latency. So in the communication system, we mostly talk about these three terms: bandwidth, latency, and throughput. Because of that reason only, I have put the slides here. And the higher the pipe width, the more blood can flow, or the more water can flow. That is clearly shown and the right side, the larger the diameter of the pipe, it can carry more data. So high bandwidth. Okay, so now with those technical basics, we are coming slowly to the topic. So I told you that in any of the IoT systems, first job is you have to acquire the data, right? Second job is you have to process the acquired data. And third is to communicate the processed data to the further processing nodes or the clouds. Now the whole block, again a cartoon which tells you this the same thing. This is MRI machine. Somebody is asking, you know that how the MRI works. So the patient has to go inside that tunnel, and after some time, imaging things are done. So somebody is asking, are we done? No. Why? Why it is taking so much time to do? Because the other guy says that Nyquist tells that we need more data. So here is the whole issue now. So when you are acquiring the data, we all follow a very powerful or very fundamental principle that we have to acquire data using Nyquist criteria. So here is the crux. Right? So if you acquire data using sub-Nyquist, if you don't follow the Nyquist criteria, then we were told that you cannot recover the signal or you cannot reconstruct the signal. For that reason only, whatever the information bandwidth you have, we have to twice that frequency, we have to theoretically, we have to sample it. But in reality, because of different issues in the ADC, we sample it using 6 or 7 times the information bandwidth. So if your information bandwidth is 100 kilohertz in the signal, we sample it using 600 or 700 kilohertz. Now, if you sample it using 600 and 700 kilohertz, then you imagine how much data you have to process, right? And if you want to transmit, again, you have to follow the Nyquist criteria because of the hardwares and the ADCs, we are oversampling the data and transmitting it, right? Your real information is in 100 kilohertz bandwidth, but you are acquiring with 700 kilohertz, then modulating that, then transmitting. So in the process, you are transmitting huge amount of data, right? Now the thing is, then somebody may ask the question that no, we are not doing that. We are putting lots of encoders in the transmitter. We encode, we compress it, and then transmit it. Yes, I agree with you that you are first acquiring huge amount of data, then compressing, then sending, right? So here the point is, can we do some simplification to this, right? First, why to acquire huge amount of data? So you may say that because Nyquist says that. Now, can we simplify that? The answer to that is yes. Recently, there are some techniques or some algorithms by which you can sample the data using sub-Nyquist criteria. You need not follow the Nyquist criteria. With less than that, twice the maximum frequency content in the signal, you can sample it. So the whole idea is there is no need to oversample, acquire the data, then compress it. In the simplified version, you can sample the data into sub-Nyquist criteria itself. So sub-Nyquist subsample data we say. So this is the crux behind your compressive sensing. So while acquiring the data itself, you acquire less number of data points, right? This is called compressive sensing in a shortcut. In a broad sense, compressive sensing means when you are sensing the data itself, you are sensing the compressed results. Okay, I think I'm clear to you by telling what the meaning of your compressive sensing. Now, if you do that, imagine you need not and the another crux in that is, even if you do that, you will be able to reconstruct the whole data clearly. Even if you don't follow the Nyquist criteria, even if you follow the sub-Nyquist sampling, you will be able to reconstruct the whole signal. So very interesting. But there is a what is a rider into this. Not all the signals you can do this. The signals should satisfy some property. Then only you can use sub-Nyquist criteria and sample it and you reconstruct it. We'll talk about those things in the next couple of slides, but this is what compressive sensing means in the nutshell. Okay. So we'll talk about compressive sensing basics, then some examples, then how to implement those things in the hardware also we will see, provided you are not bored. Okay, so a little math to start with, but I can skip this also. I will say that uh, not all the signals you can do Nyquist subsampling and reconstruct it, and to use this Nyquist subsampling into your data, the signals should satisfy some property. The property is the signal should be sparse. This math also tells that previous slides. What is the meaning of that? The sparse means you should be able to express the signal using very few non-zero values. For example, if you are taking that my signal is 50 Hertz component. If you find FFT of that, you will find only one component at 50. That's called a signal is sparse because with one component you are able to describe the signal in the frequency domain. So if the signal is sparse, then only this compressive sensing will come into picture. But we have seen that almost all kinds of signal, almost all signals, whatever you see in the real-time physical world signals, they will be sparse either in the time domain or in the frequency domain or in time frequency domain. This is being already seen by many researchers and it is all proved. So some signal will be sparse in time domain, some signal will be sparse in FFT domain, some will be sparse in DCT domain, some will be sparse in wavelet domain. When I talk about time domain as it is, frequency domain, FFT or DCT, time frequency domain, wavelet domain. So any signal you say, it will be sparse in either of these, right? Then it becomes easy to progress further. So compressive sensing is not a new thing. It was coined by Claerbout in 1970, but it was not practiced because the maths were not clear, mathematics were not clear, how it will work, how it is working. So in 1995, one paper came from the Logan. He has done very first some math he has told, but during 2004 to 2006, many papers came and the first the experimental results also they demonstrated in 2006. So these are all pioneers who has contributed a lot to the compressive sensing, and because of their analysis, there are their math supporting things, we are now able to apply this compressive sensing to different platforms. Okay, so now the business is that no more Nyquist sampling if your signal is sparse, right? So in conventional sampling, you generate massive data using Nyquist. Then we compress it like JPEG or something. In that we discard the redundant data, then transmit it. It in the mean way it is consuming high power and you have to replace batteries more often. One example is nowadays in healthcare sector particularly, there are lots of wearable gadgets which are Bluetooth enabled to the nearest computing unit, and it doesn't life is only 1 day or 2 day, right? So there also some company he has started putting compressive sensing into the signal, so the battery life has gone from 2 days to 7 days. So there are the real life, real time examples of application of compressive sensing in the IoT domain. Okay, so now the story so far is we don't need Nyquist sampling. We can go ahead with the sub-Nyquist, but under some condition. And that condition I was telling is it should be sparse in some domain. Right? Okay. So that means for certain types of signal, a small number of samples carries sufficient information to approximate the signal. That's called as, then only you can say that a signal is sparse. So when I was talking you that if the 50 hertz signal, if you do it in the FFT, then only very few coefficients carry all the information present in the signal, and with that you can manage the whole show. Now there are many questions comes into this, right? Okay, good. It sounds better. It sounds good. But how many samples are necessary to reconstruct the signal to a specified precision? Shall I take 100 samples, 200 samples? How do I decide that? What type of samples? How can this sampling be implemented in practice? And talking about all sampling requests, my ADC itself captures with 6 times my bandwidth. So how really we do it in the practice? That is the main question. Second is, can we reconstruct it with very less error faithfully, even if the samples are contaminated by noise, right? Then if noise, there are different kinds of noises are there, Gaussian, non-Gaussian, impulsive. Will it work for all the cases? There is a universal mechanism by which any of sparse signal um, can be compressed and reconstructed faithfully. These are the some fundamental questions we have to answer, we have to address before we think about applying compressive sensing to our problem. Okay. So that means it should accept samples from a variety of sampling scheme. It should succeed using a minimum number of samples. For example, if I have information bandwidth is 50 hertz, earlier I was doing 300 hertz sampling. Now, what is my best? Can I sample it using 50 hertz? Can I sample it using 100 hertz? Or can I sample it using 25 hertz? How many samples are required to reconstruct it? It should be robust when the samples are contaminated with noise. It should provide optimal error. It should guarantee faithful reconstruction. These are the main issues we are more worried. So in summary, this is what I was telling. Earlier, we used to do Nyquist sampling, then compress, then transmit. Now, both the blocks are merged, and we call it as sub-Nyquist sampling. Okay. Practically, this example demonstrates you what I mean to say sparse means. You can see in the left-hand side, there is 1 kilohertz signal in time domain, but in the frequency domain, one coefficient is enough to carry all the information. So it is, I can say that signal is sparse in frequency domain. There is another signal which is, let us see what are the content in that. The signal in time domain is shown below that. Again, if I do FFT, I get very few coefficients. So I say that the signal is sparse in the frequency domain. And once the signal is sparse in the frequency domain, I can say that my signal is equal to, this is the FFT domain. So FFT basis on FFT basis, and there are the FFT coefficients. So I can I can express my signal in this way if it is sparse in this domain. I will tell you some real life examples step by step. You'll get to know. Now this is the whole summary of compressive sensing. If you understand this, you are done. So this is my sparse signal. This can be sparse in any domain. I'm not. So I should know that in which domain my signal is sparse. Let us say signal is sparse in FFT domain. So with very few FFT coefficient, I can represent the signal. Then what I need to do in the transmitter, I have to multiply this with a matrix, random matrix, let us say for the time being, right? So if I have a signal of n samples, this is n sample signal. If I multiply this with a random matrix, right, of size m cross n, then what size I will get at the after multiplication? I will get m plus 1. Now, if this is my, for example, 512 by 1, and if I multiply this with a matrix of, let us say, 100 by 512, then resultant size is my 100 plus 1. So I am transmitting now this 100 samples only. Instead of transmitting this 512, I will transmit this 100 samples only. And what is this 100? 100 is, I am saying that I have decided that I will transmit only 100 out of this 512. I will tell you how to find this 100 also. But this is the basic principle, that you have the sparse signal, you multiply that with a random matrix of size. You define how many samples you want to transmit, multiply the original signal length, then you get only 100 samples in this case, or if you generalize it, you get only m samples. And where the m is very, very less than n. Now your job is done. So you transmitted very few samples from your IoT, but we have to extract the complete X in the receiver side. So next challenging job is how to get back this X from the Y. You have to understand a little bit of math again for this. Now I had X, I multiplied by random matrix, I got Y. This Y is going to my transmitter antenna, but I know that my X is sparse in some domain. So let us say my X is sparse in the FFT domain and psi is the FFT basis function. My X, I can write in X equal to psi of alpha. If I replace this, I get Y equal to this. And where I can say this, I can write my phi into psi is in another matrix. The multiplication of these two is A alpha. So at the end, in the receiver, you receive this. But our job is to reconstruct X. How I will reconstruct X? First, I will find what is the alpha. Alpha equal to A inverse Y. Once I get alpha, I can multiply with the basis function in which it was sparse, then I can get back X. So this is the fundamental concept behind the compressive sensing. But it has its own challenge. The first challenge is this A matrix is a non-square matrix, which is of dimension m cross n, where m is very, very less than n. It is a main challenge. So the matrix is undercomplete. So you have to find a inverse of an undercomplete matrix. It is not easy. Your general matrix inversion will not work for this. Right? So that means in the transmitter side, it is very easy. Just you have to do a matrix multiplication. But in the receiver side, you have to do a lot more to get back the undercomplete matrix inversion. So in some sense, we say that your transmitter is a dummy in case of compressive sensing, but your receiver reconstruction has to be a little tough. So you need more computing power there. But in transmitter section, there is no need to have more computations. Simply you multiply a matrix with a vector. For this reason only, it is much more suitable for IoT devices, because we don't have a powerful processor in the transmitter side, but we have a powerful processor in the cloud. Right? So you transmit the compressed samples, you reconstruct in the cloud and do whatever you want to do, all processing there, then again transmit the decision to the customer. So because of this nature only, it is finding its place in the IoT domain, right? I believe you are understanding what I am saying. If you are having any doubt, please unmute and ask me. Otherwise, it becomes very monotonous. Participants, are you there, or you just switched off and went somewhere?
Yes, sir. While reconstructing the signal,
Yes.
so is there any problem with the recovery of the sample, sir? I mean, how much?
Problem means
So if you miss any samples,
no. That
is
depends.
it
This is not lossless. It's a lossy.
okay?
It's a lossy reconstruction.
Okay, sir. And one more thing, the what
And
about
the
the
MAC value or mean absolute error or mean square error value, you have to iteratively you have to find all the samples in the reconstruction side. So that is under your control how long you want to iterate it and get the samples correctly. There's a mean square error, you have to always monitor that.
okay?
You have to minimize that error. For that, how many times you have to run it, you decide. If you are happy with less MAC, you stop it quickly. But it all iterative at the receiver side.
Yeah. Okay, sir. Thank you.
Okay. So this is all about the fundamental things about compressive sensing. Right? So slowly I told initially that we don't need Nyquist criteria, but then I put a rider. No, you cannot apply to any signal. The signal should be sparse. Second, I am telling you that you have to multiply with just a random matrix, but now I will put a rider that no, simply you cannot have the matrix also should satisfy some properties. The phi matrix should satisfy some properties. Then I will tell that this M initially I told you decide how many samples you want to transmit out of 512. Then I will tell how to choose that value, right? So these are all little maths will be there, which will help you, which will guide you to choose different parameter values of this compressive sensing. So there are now, what are the unknown things? In this, X is known to you, phi you have to define, psi is known to you, alpha is known to you, because you know that your signal is sparse in which domain and what are the coefficients. So you have to find phi and we have to find M. So we have to decide what is phi, how to find. We have to decide how to set M. And there is one more parameter which is going around, that is K. What is K? K is the sparsity factor. So how many, in the case of 50 Hertz example, your K was 1. Right? How many non-zero entries are there in that signal in some domain? Need not be time domain. If the signal is sparse in frequency domain, you plot the frequency domain, you get the frequency domain plot. From that, you can find how many non-zeros are there. If you are thinking it is sparse in DCT domain, you plot the DCT of the signal, you'll find how many non-zeros are there, right? Um, from that, you can decide what is the sparsity level. Once you have the sparsity level, you can define what is M, because there's a relation between these two, M and K. Once you have both, then you can decide dimension of phi, and by satisfying some property, you can generate the entries of the phi. Then you are done. Okay, the same thing. I can skip this slide now. Now, in principle, right? So I'm telling you that this phi matrix should satisfy some property, but in general, even if you don't want to go to the math behind that, you can choose a Gaussian random matrix which satisfies in principle inherently all the properties required for that phi. So your phi properties is set. You generate a Gaussian random matrix. Uh, then in the transmitter, it is simple a matrix multiplication. So I say that transmitter is dummy, but in the reconstruction side, I have to be a little careful because this matrix inversion I have to do, and for the non-complete, what is that? What is the undercomplete matrix? Right? You cannot apply your normal matrix inversion into this. You have to apply for pseudo inverse matrix inverse algorithm. Okay. Now, what are the advantages of this? You don't need to have any information about this signal. Yeah, I'm not worried about what the amplitude of the signal. I'm just worried about the whether this is sparse in some basis function or not. in which basis function it is passed. In FFT basis it is passed, in DCT basis it is passed, on where it is passed. Then I can multiply, I can find my phi matrix and multiply it and transmit it. So transmitter side, there's absolutely no maths, no complexity it has. Otherwise, in the conventional case, you have to acquire a Nyquist criteria sampling, then you have to apply JPEG. JPEG itself is complicated. So transmitters should have enough powerful processor to do those compressions. But here we don't need that. Okay, so there are some design steps. I will not go detail into this. You will, if I go, you will sleep. But I will say the things known are this. This is also known to you. The dimension n is known, but m we have to find out. And m is normally we follow this relation. M is greater than or equal to 2k, and k is known to you. K is sparsity factor. So you can find m. From m, you can, once dimensions are known to you, you can generate a random Gaussian random matrix to get phi. Then all the things are done, right? But there are different techniques are there, different methods are there to have different types of phi. But in general, for the beginners, you can choose that your phi is the Gaussian random matrix size m cross n, and you can proceed it. So you need not worry about detailed mathematics. So actually, when I talked about this, the property name is restricted isometry behavior, and your Gaussian random matrix satisfies that. That's what I say, that you blindly can take a Gaussian random matrix and apply compression to your signal. Okay, there are different ways to do this. Apart from your Gaussian, you can have Bernoulli distributed matrix, you can have Topli's matrix, you can have a circulant matrix. There are different techniques are there to choose the sensing matrix. You may ask, what is the difference between all these things? Why we need all this? Because in the transmitter side, if you choose a random matrix, that information should be available to the receiver side, right? So how we will communicate that to the receiver? That's the question. So some people will say, okay, what is the big deal in that? I will generate a seed, and that seed I will transmit to the receiver. Using that, you can find phi, and from that you can find the matrix, because for this getting a matrix, you need all these things. Your a matrix is in the receiver side. So to generate a, you need phi and psi. Your phi is random, Gaussian random in the transmitter. How you will generate this again back in the receiver? That's the question. So if you have random, then you have to send the seed to the receiver, and that guy has to regenerate this phi and use it, right? That is a little complicated stuff. Otherwise, if you have a deterministic phi, it is known to you from well in advance. You know that what is your phi. The same phi you can use in the receiver, and you can do the job, right? That's why there are two classes of techniques, two different class of techniques are there, random and deterministic, by which you can generate the sensing matrix. Okay, let's take an example. This is your original signal, which is sparse in DCT domain. If I plot DCT coefficients, I can see very few coefficients are there which are non-zero. So I can say that in this case, my sparsity level is 5. There are some physiological signal like ECG, EEG, PPG, and respiratory. All are sparse in DCT domain. It is all known. All other signals, then your biological signal, all are sparse in FFT. Okay, now we know how the things are being done. What are the design steps? Now let us talk about two different ways how to do it. I am telling you that at the ADC itself, we have to compress it, but those ADCs are not available to us, right? So whatever the ADC we are getting, they are all So the current ADCs are not equipped with the compressor sampling, right? The conventional ADCs are there. Then in the digital, there are two types of encoder, analog or digital. In the digital case, you get the data from the ADC, then apply phi into that in your processor itself. This is inside the processor, and then get it. Remember, you are not saving anything here. So this XC is a full Nyquist sample signal. But before transmitting it, you are compressing using this and transmitting. Whereas in analog signal, analog compressive sensing, in your ADC, this will be inside the ADC. So when you take output from the ADC, the signal is already compressed, right? Many a time people say it's AIC, analog to inversion converter, right? But in practice, they are not there as of now. It will come soon because the field is evolving now. So as in digital engineers, we all talk about the below one, we get it, the data from the ADC, but then we compress it and do all these processings. But there are some companies like Intel, they have used this analog CS, they have fabricated their own ADC based on the method, and they have proved that there is a savings of 30 to 40% power consumption in their IoT products. Okay, the same thing is now expanding to other biomedical related IoT products. You have many sensors. So if this is analog compressive sensing you are doing, then you ADC itself, you compress it, then you transmit. So this is your compressed signal coming in the channel. Then you have a reconstruction engine in your processor. You apply different reconstruction algorithm to get back the original signal, then do whatever the processing you want to do with that. So you save a lot of communication bandwidth and you save a lot of transmitter power using this. Because bandwidth is also equally important nowadays. The 5G, 6Gs are coming, they will operate at very high bandwidth. So you need to save the bandwidth also. Less bandwidth kind of technology if you develop, that even more lasting. Okay, so recovery process is the crucial thing here. Let me again revisit the same slide. We got this part and we have to find alpha, and once you find alpha you can reconstruct it because this is known to you. And this finds the A inverse, the A is undercomplete, so general matrix inverse will not work. There are some specific specified class of reconstruction algorithms are there, which is being used to reconstruct the original samples from the compressor samples. I will not go to the maths of reconstructed algorithms, but I will tell the class of algorithms which are being used to recover the signal when the compressed samples are contaminated with the noise, because this comes in the channel. So this guy will see compressed samples plus channel noise. So this is a noisy compressed sample. So you have to apply your algorithms to reconstruct the original samples in the presence of noise. And there are different kinds of noises are there. You have to see which kind of noise characteristics this whole thing is working. That is a different research problem itself. Okay, so now we are talking about the recovery algorithm. Any doubts so far, the participants? Please participate. If you don't participate, I may be thinking you are not in front of your system. Just I am talking. Will not feel good, no? Only one guy talking is not good. Okay, I could see around some people are there, but they decided not to talk. Right, let us proceed. So there are algorithms like matching per suite, orthogonal matching per suite, very different class of algorithms are there. Those who are interested may look detailed into that, which helps to reconstruct the signal in presence of noise. Yes, so now the whole thing is boils down to your input signal, your random matrix, you multiply it, this is your transmitter. Then the receiver, you receive this, you have informations about your phi and psi, you reconstruct it. Essentially, you are reconstructing your alpha values, and from that you get back your x. So this x and x prime, if you compare, they are good agreement in sense. That this is not a lossy, this is not a lossless, it's a lossy reconstruction, but with good agreement between the input signal. There will be good agreement within the.
Excuse me, sir.
Yes.
Sir, compressive sensing can be implemented in in which layer, sir?
This is in the after sensing layer. After sensing, what you have? Processing layer, right?
Yes.
There. Before it goes to your edge. In the edge node, edge layer is can be done.
Okay, sir.
Am I clear?
Yes, sir. Yes, sir. Thank you, sir.
It will be in the edge layer. The edge processing, I can say.
Okay, sir.
Okay, fine. Okay, so earlier our conventional was in the conventional way sensing then compression, but now both are combined together and we get the benefit of less power and those things. Okay, now this is all about if a signal is sparse in time, in a temporal domain. If your all physiological signals are temporal, no? Because with respect to time only we record it. So they are temporal. But let us say in a sensor network, you want to apply it. So sensor network sensors are deployed spatially, right? So this algorithm also can be extended to a spatially sparse signal. What is the meaning of that? The meaning is, let us say this one, right? You have many sensors at different parts of your body. You can imagine that they are placed at a different location, different sensors. So at time t equal to t0, you have different sensors spatially deployed. You can explore the sparsity in this way and you can compress and send it. And if you are exploring sparsity in this way, in this dimension, this is a temporal sparsity. You are exploring sparsity in this way, this is spatial sparsity. So if they both are sparse in, if they are sparse in both the domain, then you can apply joint sparsity and still reduce the number of samples to be transmitted. So in this way, a lot of research papers are there, but we can work on this and reduce the power consumption and the bandwidth of the channel. So sensor network is mostly on the sparse, spatial sparse, whereas in one-dimensional signals are all temporal sparse units. Okay. This is what I wanted to tell. If 1D signals you can see in the temporal domain, they are sparse in temporal domain. But if you can explore that, they are also sparse in this way. They are all spatial. Accordingly, the reconstruction algorithms are you have to tune up and get the reconstructed signal from each sensor nodes. Okay, now earlier we were talking about this is some question somebody was asking me just before some time. Earlier in this layer we didn't have the CS based stuff. Depending on application you have to choose. somebody can say that, okay, from sensor I collected the data, in edge layer I am I am compressing it, right? Then transmitting the compressed sample to the cloud. Somebody may say that, no, here I have a small IoT processors are there. I will compress here itself. Yes, you are welcome to do that also. So depending on your application, where it need to be compressed, either it can be compressed in IoT node itself, or if you want to compress at the edge layer, you are free to choose. The benefit what you will get if you use compression in the edge layer is that from many sensors you have data here. So you can think about applying spatial sparsity, and you can do temporal and spatial sparsity, both joint compression you can use, but here only you can use temporal sparsity. That's all. So this is your CS IoT architecture. When we started the talk, we were talking about the normal IoT architecture, but now it is all compressive sensing based IoT architecture. So you have a CS based acquisition, you can have a CS based compression here. Some people will say that, no, I will acquire at this part using compressive sensing, but I have to take decision, some preliminary decision at the edge. So I will reconstruct here and do. You're welcome to do that, because normally edge layer processors are little powerful than the processor available here. So depending on your application, you can choose where you will compress and where you will reconstruct. Right? Or somebody can say that, no, I will not take any decision here. All compression samples I'll send to the cloud and take decision. That's also good. You will save a lot of bandwidth in this region. So depending on your requirement, you can choose where to apply this compressive sensing reconstruction in your application. I hope it is clear now. Someone is asking this question.
Sir, one of the questions, sir. Since this compressive sensing means just we are reducing the data samples, right, sir?
Right.
So here, can we connect this technique in the machine learning or deep learning?
Yes, there are some works are going on in that direction also.
Okay.
Can you retain the information or from the compressed sample can you train the network and get the um, final output? People are working on that line also. You need not reconstruct and get it from the compressed samples. For example, I will tell you, if you want to know a person is there or not, and you have taken some data and you use compressive sampling into that, I think you can find out from the compressed samples the person is there or not. But if you want to know who is that person, you need all details. Then you have to reconstruct the signal. Then only you can find who is that. Is Kiran or is Abath or is something else. So if you want that, then probably you have to reconstruct. But course level information, if somebody is there or present or absent, those kind of things you can do using compressed data. There is no need to reconstruct. But there are still people are working on can you train the network from using the compressed samples and get the information what you want to do. There are works have been started in this area recently, I will say. Is it answer your question?
Yeah, yes, sir.
Okay. Okay. So now this thing will become CS enabled IoT architecture. So you can appropriately use where CS need to be added. Okay. Now there is something somebody talks about distributed compressive sensing, right? The meaning is that you have many nodes in the network, right? Can you receive compressed samples and can you reconstruct the signal also in a distributed plan? Everybody will receive chunk of the data and they also will be doing a part of the construction. At the end, you get the complete reconstruction. Again, very recent topic, few works have been going on. And there is another factor that if you don't know this sparsity factor, can you still find out from the data, or without knowing about sparsity, can you reconstruct, right? There are all challenges, and recently the works are going on in this direction to apply compressive sensing in different domains. So this is your, again, I repeatedly tell you this, that you have sensing layer with the below, then you have an edge layer, then you have a computing layer. Normally, depending on your application, we choose where to use compression and where to use reconstruction. So we at the University of Hyderabad work on implementing this reconstruction algorithm on FPGA, because they are a little computationally complex. So one student is working on how to implement it and with less area, less high frequency, less area, less time, with low power consumption on the FPGA. Okay, there is one more concept which also is integrated with this compressive sensing, that is security. Because at the beginning we were talking about the security also, right? So if you want to have secure, then you have to encrypt this data before it goes to the antenna, transmitter antenna. So if you apply compressive sensing, you need not do separate encryption. So with compressive sensing itself, there is a encryption going on, because you are multiplying your signal with a random matrix, right? If that randomness is, it all depends on how random is that. If that is highly random, then security is enabled into this, right? So there are different ways to generate a very sophisticated random numbers, and if you use those techniques and generate random metrics and multiply the data itself is secure. You need not do. The first level security is inbuilt into this. Of course, if you want to have different protocols, then you have to bring those protocols. But what I wanted to say is your first level security is inbuilt into this. Okay, there are different challenges. One of these challenges is implementing these algorithms in a very area constrained, speed constrained hardware. One of that is FPGA. So we were doing some work on implementing these algorithms on FPGA. The next 10 to 15 minutes, we talk about that with the case study. Let us say there are some temperature data, right, from one sensor, and you want to transmit it using your IoT and compressive sensing enabled IoT system. So we have to find first what is the whether data is sparse or not. We have applied this data to DCT, and when we plot the DCT coefficient in a descending order, we see that only this many coefficients are okay. Prominent coefficients are very few, I can say, right? So based on this, we can choose what is the sparsity. Let us say I will choose sparsity equal to this much. After that, they are close to 0. I can neglect it. So here I will choose my k equal to 20. Accordingly, I have to choose what is my m value, because n is already decided. I am acquiring 512 samples. Okay, so in this case, k is not 20. I had zoomed it and I found that 17 will work for me. So sparsity is 17. Once sparsity is 17, I told you have to choose your m value. Minimum is m value should be greater than 2k, but there is some way to calculate it, and I am getting using those calculations, my m value should be 94. Anything more is good for me, right? So my n is 512, but with 94 samples, I should be able to reconstruct it. So this is my complete signal. When I multiplied my signal with the random matrix with the dimension 94 into 512, 94 or this is 180, sorry. So I have chosen 180 as the M, When I multiply this 512 x with the 180 cross 512 multiplied with 512 by 1, this is my signal, this is my 5, I get 180 cross 1. So this is the signal I am transmitting. This is my original signal. This is my compressed signal. How many samples I have? 180 samples I have. Right? So it saves a lot of bandwidth, I can say in that sense. And in the reconstruction, when I apply this different algorithms, I will be able to, there is a little bit of scaling problem in this slide, but I rectified later on. But you can get back your whole signal, 512 signals from that 180 signal, 180 samples. So this only demonstrates you that, okay, this is your original signal, but you can multiply with random matrix. Those parameters we have chosen carefully. This 180 came from a calculation. And if you transmit this at the receiver, I can reconstruct the whole thing. So this is all about your compressive sensing reconstruction algorithm and how it is working. Okay, this is another example which tells that I have many nodes, and across the nodes, if I want to apply spatial sparsity, how to get it? This plot also tells the same thing, that if you have joint sparsity, you can apply and reconstruct the whole signals from the different nodes. The signals are there, you can see. They're all matching in this way, original and recovered, you can see. So they're all working. That means you have a different nodes at different places. You can compress it and transmit it, and you can get the signals correctly at the receiver side. There are some challenges if your parameter to measure is having different sparsity. In one node you are measuring humidity, other node you are measuring temperature. Temperature may have a sparsity 18, humidity may have a sparsity 15. These are the challenges we have to see how to address it. But there are some algorithms, there are some research going on how to address this part also. The interesting thing is this algorithm need to be implemented on a hardware. Right? And as I told you that we are working mostly on the FPGA side, and one student has implemented this using Xilinx Zinc. You can see that here is this OM reconstruction algorithm IP he has created and interfaced, and we are getting this. We are able to reconstruct it exactly in the EDK platform. But the whole idea is how to apply different architectural technique to this reconstruction algorithm, so that quickly and with less resources you'll be able to reconstruct the signal. Okay, so this is all from my side. I believe you are still at the same place from where you started hearing this lecture. There is one popular cartoon here which tells that, okay, now there are smart washing machines are there which will be switched on and off remotely, but can the washing machine collect the cloths automatically from the room and put it in the washing machine and clean it? Probably next level of thinking is this. So there will be a robot which will roam around the room wherever any cloth need to be washed. You will smell it or get something from that and pick it and put it in the washing machine. So this is the next level of IoT. It will come. Probably all of us will experience these things. So thank you all for attending and listening to my lecture. Thank you. I have this much to talk. Now it is open for the discussion. If you have any questions, please ask me.
Sir, one more question, sir, from the participant. So,
yes, please.
Somebody is asking about the adaptive compressive sensing, and where we can use in what kind of applications we can use this.
Adaptive compressive sensing in the same. You see, when data is coming continuously, sometimes the sparsity changes, right? So how to use those, how to incorporate those things into your data? Data statistics doesn't remain same throughout in a longer period. If for any application, data statistics changes, how to bring adaptiveness to this, but exact math, exact algorithm, I don't know, but this is the concept behind. Yeah, this is from my side.
Sir, one more question, sir.
Yeah.
Sir, as you said, this compressive sensing will act like a kind of encryption, right? Because
It is not X like encryption. Compressive sensing enables first level of security.
yeah. So
Because of that random matrix multiplication.
yeah. So do we have any comparative study of this kind of encryption and other like crypto algorithm encryption, sir?
No, they're all working, coming recently only you have to see the literature, but it, it enables first level of security. I'm not saying that you should not use any like SBox or kind of protocol into that. That those will be there, but it is an extra layer of security it has. Anything else?
క్వశ్చన్ చెప్పండి ఇదేం వినలేదు అసలు.
Let me go to that main window otherwise. Where is that? Hello, I'm there.
Yes, sir. Yes, sir. You're audible.
Yeah, please. Yeah. Okay. So now I am here. You can ask any questions directly. I can see the chat box also.
Sir, may I know some of the applications related to the
Applications are, you see, any IoT, anywhere you want to transmit data from one place to other place, this is used. This is general, so general. If you want to transmit data from one place to other place, you compress it instantly. That's all.
Okay, sir. Okay.
It's a whole very wide application it has. This is like a tool.
Yes, sir. Yes, sir. Sir, do you suggest any kind of tools or the platforms for the students where they can exercise such kind of scenarios or to test?
Initially, they can try with the MATLAB, but later on, there are some network simulators are there, right?
So
NS2
NS2
or NS3. I hope that allows to include this kind of algorithm in each node level and run it.
Okay, sir. Yeah. Thank you, sir.
Any other questions? I can see 15 number when we started, but now it is 22.
I request the participants, if you have any questions, you may please. Shyam Sundar, sir. Sir, will you advise us like kind of a list of projects on these aspects so that we can guide the students to go ahead?
Project, you see, if you want to monitor, let us say, continuously temperature in a room,
Sir.
right? Which
Yes,
is
sir.
IoT, any IoT project you have where you are transmitting data to the cloud and does some or server for processing. You in that processor in the IoT you have either ARM or Arduino, Raspberry Pi, something will be there, right?
Yes, sir.
Then you do this y equal to 5x, that's all. You are now transmitting instead of transmitting the x, you are transmitting 5x. But then you have to save that x. It is not that sample by sample you are compressing. You have to save that 512 samples, then apply, then block. It has to be done in a block wise.
Oh, sure, sir.
Yeah. So any IoT application, it is suitable.
Oh, sir. Thank you, sir.
Okay. So if there are no more questions, I think we can end the session here.
Yeah, sir. Any more questions, dear participants?
Nowadays, in this online, either they are not attending or they decided that they will not talk to uh, the same thing where you see many of you are faculty. I know that, and the same kind of frustration we get when we teach in the class online and no response comes from that side, right? So it is not we should also realize that part, correct?
Yes, sir. You're true, sir.
Yeah.
But the session is very impressive, sir. We before and all we don't know like what the sensor
Okay,
data.
let me put a query now that after listening this talk, still how many of you are not aware of what is compressive sensing?
We look after the responses. I think we should not receive anything because they know now.
Okay, now I'll ask the another question. How many of you are aware of compressive sensing now? This will tell you the real attendance, madam. So how many of you are aware of compressive sensing? Please post it in the chat box. You see, looks like only one person is there in the class or the seminar. Participants, if you are able to listen me, if please respond to this chat box query. How many of you are aware of compressive sensing now? At least what is compressive sensing? See, only one. That means only one person is attending. Okay, okay, two. Yeah, so this is the reality. Okay, madam, then I believe we can, what the one question game? For efficiently acquiring and yes, I am not asking definition, but I'm just asking you are aware or not, yes or no kind of answer. Okay, fine. I am happy that some of you could say that now you are aware of this what is compressive sensing, because when we started everybody said no. Now at least those who are listening to this talk, they are saying that yes, I understand it. Okay, thank you all for this patiently listening to this talk.
Thanking you very much, sir, for accepting our invitation and shared your knowledge towards the compressive sensing, particularly towards the IoT application. And you just answered for the doubts like how to proceed with the different techniques and algorithms, and what are the tools which can be get it patch up, and how can we go extended by using the algorithms and all. And very nice session, sir. We are honored to have your session, sir. Thanking you very much.
Thank you, madam. Thank you, KL University, for giving me this chance to talk with the participants.
Yes, sir.
Thank you.
Thank you. Thank you very much.
I can leave the meeting now.
Yes, sir. Yes, sir. Kiran sir will be in touch with you, sir. Thank you, sir.
Okay.